this opportunity to give a talk at your seminar. So my name is Dmitry Lьвов. I'm a PhD student at UK Pekola's PICO group in Aalto University. Previously, I worked in Valery Rizanov's laboratory for superconductivity in Chernogolovka. So I know many of you from those times. I would like to give a talk about Qubit thermometry. It's my current project. I started it like half a year ago, approximately. So, and that's why it's very important for me to get some feedback from more experienced colleagues, of course. So the idea of this project is to use the Qubit as a thermometer. In some sense, Qubit can be considered as an ideal thermometer because it has a very small heat capacity, which is just one photon, which can be used to excite it from the ground to from ground to excited state. Yeah, and
so correct to say that it's heat capacity. Heat capacity is something different, isn't it?
Well, so I would say that in thermometers there are a few very important crucial parameters, right? And so it's better to have the minimum heat capacity. And in that sense, well, of course, we cannot say that in principle there is a temperature in a qubit, but yeah, what energy it can kind of acquire is just one photon, right? Well, okay, several photons.
That's a limit. That's a limit.
Yeah, limiting case. Yeah, of course.
And temperature is very well defined in a two-level system.
But it is not. I mean, it's temperature only when it is coupled to some bath, to my taste at least. So you can always define an effective temperature for a two-level system.
Yeah, but it's strictly defined. Moreover, it's just distribution of.
It is the distribution, yeah. Mm-hmm.
Mm-hmm. Okay.
Okay, and so there are a few papers about like different things in Qubit which can be measured, and they can be used to describe the effective temperature. For example, on the right, you can see the paper where the authors used the population distribution to measure the effective temperature. Well, okay, they measured this independently, but there is a clear dependence between the temperature and the population distribution. Well, another paper is where they saw authors they can resolve the photon number of in a resonator, which is coupled to a qubit, and they also can define, for example, the distribution of coherent photons which come from like a source, or RF source, or a distribution which is caused by some like population of thermal photons. So there is actually a question: what can be used for more efficient thermometry when we use a qubit? So the realization is following. Like we have a transmon qubit, which is connected to a quarter wavelength readout resonator on one side, and on the other side, it is connected to another resonator, which is coupled to a thermal bath. A thermal bath is a mesoscopic line, a strip of normal metal, which is connected to superconductors by tunnel junctions. And so with this NIS junctions, we can at one time control the temperature and measure this temperature. So that's how we have like several ways to know what is the effective temperature in our system. So a few words about in NIS thermometry in principle. So when we have NIS contact, we have in normal metal like density of states which is more or less constant, and there is Fermi distribution of electrons. And on the other side of the barrier, we have superconductor, which have this BCS density of states. And so applying the voltage across, for example, symmetric structure, we can at the same time extract hot electrons from the normal metals and put there some colder quasi-particles. And so we create some non-equilibrium distribution, which effectively acts as like lower effective temperature of normal metal. And applying a bit different voltage, we can heat, so increase this temperature. And so, for example, on the plot, you can see how the cooling power of this NIS contact depends on the applied voltage. So, and now to measure the temperature, we can use just the IV curve of an NIS contact. So on the left plot, you can see IV curves for NIS contact at different temperatures. And to measure the temperature, we can fix the bias current at some value, and then if we change the temperature, the voltage across this junction also changes. And so using this thermometry, we can connect this temperature with this voltage across the NIS junction at a fixed current bias. So these are some typical structures that I used in Pico group. And so, first of all, on the right-hand side, you can see how this thermometry is done, the measurement setup. So we have like 4 tunnel NIS contacts and 2 superconducting banks with clean contact. So they can be connected, for example, to our resonator. And so in the middle, we see this normal metal strip. So we use 2 contacts to apply this current, bias current, and then we use another contact to actually measure the. And so.
Can I ask you a question about this geometry? So it looks like you are hitting the wire from one side. I'm not sure how it works, but measuring the effect on somewhere away from the point where it's hit. So do you suppose that all electrons are distributed homogeneously?
Can I answer this? So yeah, so in the diffusion in a copper strip is very fast as compared to electron phonon coupling, for example, in this case. So it really is extremely uniform temperature in this case.
So the assumption is that it's uniform, and it's
not only assumption, it's really a measured fact.
Okay.
So to a high degree, it's really uniform.
Okay, good.
Okay, and so on the right plot, we can see the range of the achievable temperatures. For example, at roughly 130 millikelvin bath temperature, we can cool down down to, I guess, 110 millik, and we can heat up to 350 millik. So that defines more or less the range of temperatures that we can locally achieve. So a few words about the fabrication that we use. We use substrates with high resistive silicon. So the resistivity is more than 10 to 4. Oh, sorry, not kilo ohms, but ohms. Yeah, then we make the atomic layer deposition of aluminum oxide of 40 nanometers. Then we do magnetron sputtering of 200 nanometers of niobium. Then to form the ground planes, for example, transmission line, resonators, and just big contacts, we use negative EBL on ARP resist, and then we etch niobium away. So in this process, aluminum oxide also acts like a stop layer. Then to make a squid, we do another EBL. We use MMA, PMMA resist, and two-angle electron beam deposition of aluminum and oxidation. So to form NIS structures, we have to use third EBL, and there use three-angle electron beam deposition of aluminum and copper. So this is like a equivalent circuit of the structure that is planned to be fabricated and measured. So there is in the middle a transport qubit, which is coupled with two resonators. One of them, which is designated by blue color, is connected to a transmission line, and the other one, the red one, is connected to a thermal bath. So which is this normal metal with NIS contact. So these are design parameters of the qubit, which I wanted to get. So the 0-1 transition frequency is should have been 6.5 gigahertz. And for transmon qubit, the unharmonicity is minus EC, which was about 200 megahertz. So then I made quite big couplers. So the
can I ask you some questions? I'm not sure. Probably you will have the data. So when you are coupling something, okay, for example, two-level system to some bath for qubits, for example, for conducting qubits, what is important? The coupling strengths, but the coupling strengths to the bath or to the line is characterized by relaxation time, okay, the time which characterizes the or defines the escape of photon to the bath. And among your parameters, I don't see it, but it's the most important thing. And you need to compare this time with or rate with the relaxation rate of the qubit, non-radiative relaxation rate of the qubit.
Yes, that's right. But in the structures, I didn't add the thermal bath yet. I just
no, this thermal cavity is written thermal cavity.
Yeah, but
left hand side.
So there is just a resonator without a thermal bath.
Okay. So does it mean that you have two resonators from both sides?
Yeah. Yep.
And you characterize it as coupling strength G for both of them, right? I see
Yep.
only one G in the table.
Well,
another one.
There is like thermal cavity and readout resonators. On my structure, I have
thermal cavity. I see. Ah, okay. Yeah, I see it. Two. Sorry. Two columns and two elements. Sorry.
No problem. Yeah, you're welcome. So yeah, I wanted the tuning to be quite big. So the parameters of the circuit would be like more robust to the fabrication errors. So yeah, and there are a few words about that. The most difficult to achieve is the reproducibility of our Josephson junctions, because they are defined by many parameters in the fabrication, for example, by EBL parameters, by the development process, which is always a bit different than by argon milling, which can be also which parameters can also drift away because like many users in the clean room use the tool, and finally by oxidation parameters. So I wanted to keep the tuning about 1 gigahertz, and so yeah, so on this plot I wanted to stay far away from this points where the dispersion goes to infinity. So like on the far left side or on the far right side. Yeah, so here is the photo of my sample. So the transmission line on the bottom, then 4 readout resonators. These 4 readout resonators connected to separate qubits, and so there is one bare resonator without a qubit to make sure that to see its parameters actually, to for example like Q factor. Then one of these qubits is connected to another half wavelength resonator, and on the top there are a few test structures. So they are essentially the test squids and aluminum niobium interfaces to measure resistance that there is clear contact between the squid and niobium ground. So here is the photos of the qubits. So like on the bottom it's like big capacitance, and here's a photo of the resonator without a qubit. So before coming to the experimental results, I'd like to discuss a bit the COMSOL simulation of these resonators. So after putting this design to COMSOL and running the search of eigenfrequencies, I found that there are some modes that are not related to the resonators, but to some other structures. For example, there is one resonator, one resonance which is referred to the transmission line, and one parasitic. So after the simulation, I understood that the couplers have a large influence on the resonator frequency. So there's a shift of the resonator frequency almost 1.4 gigahertz, which is caused by this coupler. So here you can see that there are like 4 resonances caused by resonators, and there are like 2 additional. One of them is caused by the transmission line, and another one is some parasitic mode. And I'm not sure how console can define the quality factor, but we can see that quality factor for this parasitic mode and transmission line mode, they are much lower than other resonances, and so they have a quality factor of like of order 1 to 10 compared to a few hundreds for other resonances. So here is the plot of this simulated resonances. So well, what is a bit strange for me that the amplitude of this dips, it's very low, and it's kind of less than 1 dB, and that's a bit strange, and I think that it is somehow connected with the way COMSOL simulate things. So if there are people who know how to use COMSOL for the simulation, I would be glad to discuss. Yeah, and so there are a few more questions about COMSOL, for example.
By the way, did you use this Sonnet already? Because this is what guys use now.
Yeah, they not yet. Well, I'm going to use it. It's like intuitively better and gives better results. Yeah, because for example, in COMSOL, if you sum up the S21 module squared with S11 module squared, you don't have 1. It's near the resonances. It's always much lower than 1. So there are some energy losses which are not caused by the structure as you design it in the COMSOL. Yeah, so it's a problem, obviously. And in Sonnet, it's not like that. It's different. It's fine. Maybe these problems, they are caused by this finite size of the mesh cells. I also noticed that the sweep step in the simulation also makes a huge influence on the results. Okay, so and now you can see this S21 parameters which were measured on the real structure. It's the red curve, and the simulated peaks are drawn in black, and so you can see that there is one peak missing in reality. So it's the highest frequency. And well, yeah, when I looked at the optical microscope, I could see that there is a short in the coupler. But other resonances, they are more or less coincide with the simulation. So the lowest frequency is the longest resonator, which is on the right, and it doesn't have the qubit. Then there are 2 qubits, and like the highest frequency that was measured, it is the frequency of the resonator coupled to a qubit and another resonator half wavelength. So this is results of the one-tone spectroscopy of the barrier resonator. The quality factors. Yeah, I think I used the package written by probably Gleb Fedorov. Yeah, and so this in the bottom you can see a table with the results. For example, the Q factor Q loaded is about 3,000, and the internal Q factor is about 7,000. Yeah, and there is no dependence on power or sorry, the cat something. So yeah, so it's obviously not connected to any qubit. Then the next resonator with intermediate frequency of approximately 6.5 gigahertz. I'm sorry, it's not chi. Yeah, but we can see this like a very big influence of the qubit on this resonator. So this frequency changes by 40 megahertz. Yeah, and here on the right plot, we can see this shift depending on the power. So at higher powers, as I understand it, the resonator is overpopulated and don't like it doesn't sense the qubit anymore. Yeah, so these are fitting results. So again, Q loaded is about 2000, Q internal is about 4000. Here is this two-tone spectroscopy. Yeah, so the 0-1 transition here, it's approximately 1 gigahertz lower than it was planned. So it's not 6.5, but 5.6 gigahertz. And so the tuning is about 800 megahertz. So then on the right side, you can see the two-tone spectroscopy depending on the power of the first tone. And this distance between the peaks, it can give us the value of charging energy, which is more or less what was planned, 200 megahertz. Yeah, and at higher power of the first tone, there are a few more resonances visible. Well, I'm not sure what they are caused by, but yeah, there are like a few more transitions visible on the spectrum. So
Mitya, can I ask you, on the right plot, color plot, there are some ripples.
Yeah. So
what are they?
Well, I asked my colleagues, and probably that is well, this ripples, they vanish if I lower the power of the VNA. And so maybe I can sense the number of photons in the resonator, but
number of photons in the resonator. Okay, this that would be kind of interesting. So you can analyzing these ripples, you can understand what's the actual temperature of the resonators, right? And if it's the appropriate distribution of the photons.
Well, yeah, that would be interesting. I didn't plan to actually to observe this effect. Okay, so and this is the resonator with the qubit, which is okay, the one-tone spectroscopy of the resonator, which is coupled to a qubit, and the second resonator. So here, this frequency change is smaller. It's 30 megahertz, but is again significant. So the quality factors are roughly the same, 2000 loaded and internal about 8000. And so here is two-tone spectroscopy, and yeah, the tuning is more than 1 gigahertz. The 0-1 transition is 5.5 gigahertz. Well, and yeah, again, EC is about 200 megahertz here. Maybe I should stop here to yeah. So here I reduced the power of this VNA to get rid of this ripples. Actually, I could also see them And so if we enlarge this part of this two-tone spectroscopy, we can see that the height of this peak, it is significantly reduced in some region, and this is probably caused by this lambda over 2 resonator, which kind of sucks some photons in this range from the qubit. So we kind of induce this transitions, but we don't see them in the S21 parameter of the transmission line, because these photons, they go to the second resonator. Yeah, so, and in principle, this resonator frequency, it was designed to be 5.5 gigahertz, but it's like more 45, so it's more or less as planned, as designed. Yeah, so here are some results. The design parameters compared to experimental. So the biggest error was in this resonance frequency, and that was actually caused by these big couplers. I didn't know how to simulate them when I made this design. Yeah, so and then the difference between the design Josephson energy and the real Josephson energy which I achieved, it's also significant, like 1/4. Yeah, so yeah, and I think that the coupling between the readout resonators and the qubits, it's also like 4 times larger than I wanted it to be. Yeah, so I think that's more or less all. Thanks. Well, yeah, and further work should be with maybe trying to measure the population distribution by using pulse measurements. Then I also have to add thermal bath, and I'll have to go on with the simulations, because well, COMSOL can give approximately good results, but not very accurate, let's say, and some of them shouldn't be trusted. Yeah, thanks.
You can ask questions.
Yeah, of course.
Mm-hmm. Can you kind of formulate what's the goal of the experiment? So you have 2 resonators, and you have 2-level system coupled to the 2 resonators, right? And what do you want to observe then?
Well, first of all, the idea was like in this experiment, in this paper, thermal and residual excited state population in a 3D transparent qubit. So to measure the population distribution, which depends on the temperature of this thermal bath. So yeah, but at the moment there is no pulse measurement setup in the lab, so maybe it's better to use some other technique of defining the temperature. So for example, as in this paper, where we can see this average number and distribution of the photons in the resonator.
So the first question is really, if this, since we can control this local temperature there, does the qubit follow? Does the qubit population really follow this local temperature of the bath that we have there on chip? which has not been done up to now.
Right, but okay, my question is that in principle, the resonator coupled to the two-level system, or maybe not two-level system, but the system you have, this transform, right, with some anharmonic oscillator.
Right.
That's quite straightforward. Can be straightforwardly calculated with, for example, Qtip or some. Well, maybe you can do it by yourself.
Yeah, one can do it even without any commercial software, of course.
So just a simple kind of equilibration of the system would be too much kind of straightforward again. But maybe some dynamics would be interesting, or some this kind of photon distribution in time, some how it's happened.
Yeah, and then
a little bit more complicated dynamics. Yeah.
Exactly. So the first thing is, of course, the sanity check, whether these follow each other. But there have been a lot of proposals in literature about using different protocols for the qubit to really use it as a fast thermometer. So that's kind of the general
fast thermometer. Okay.
Yeah. Yes.
Yeah, and
you said a lot of things about this engineering simulation rather than physical. So console and other things, they kind of simulate how these resonators work and etc. But I would say that the most important thing is to see how this quantum physics takes place in the system.
Yeah, sure. Well, I'll have to learn it. Yeah. So, and I just wanted to mention that there is this theoretician Gershon Kuritsky who has some proposals for this, like an enhanced precision of low temperature thermometry.
Yeah. I mean, this is kind of the first part. That's why I think this whole session was organized. That what are the ways of really determining this population in the effective way in the measurement. Because this is kind of the first structures that Mitya managed to fabricate and measure in the lab, which is of course nice in this. We started relatively recently, so it's to my mind it's a quite nice that something works now already.
Yeah, the complication here is that the photon number, that's actually, okay, I don't remember exactly this experiment, but this is anyway the qubit coupled to the resonator. And the question is if we find, or you find the population of or photon number in the resonator rather than the whole system somehow involved in this. I don't know. Or maybe resonator, yes. But you also warm up a qubit. So for me, it's difficult to imagine. So you do something with the qubit, but eventually you measure population of the resonator. With this non-ideal qubit already populated somehow. Okay.
Yeah, and then there are these different regimes, of course, depending on how strong is this coupling between the qubit and the resonator, and then how low is the quality factor of this resonator because of the bath that we put there. So then what it really measures depends on the hierarchy of these couplings.
I think I mean, using it's actually better to use language of the relaxation rates of all systems and coupling lengths and this interplay between these two or two or three parameters is important. And also effect of dephasing, by the way, in the qubit. Okay.
So maybe more questions.
So one question is if you have some project for students. I mean, if you can do. You're a PhD student, right?
Yeah.
Yeah. So in some projects for master students within this bigger project.
Well, I'm not sure. Maybe it's a question to you.
Yeah.
You both.
Yes, this we can think separately. I think there's already some interaction between Sasha Strelnikov and
very good
about this really to analyzing the circuit. So,
yeah, that's my point.
Yeah, sure. I mean, maybe Oleg, we should discuss this also in separately, because we also discussed about this other project. So just to have the interest. If you want, we can talk about that separately after. Yeah.
Okay, so
so I think one of the, as Mitya told, we are not so much familiar yet with many of this type of measurements. Is that what is the most straightforward way in this structure to do this sanity check of the temperatures? So one obviously does not need pulse measurements for that to kind of confirm whether the temperatures of the temperature of the two-level system is the temperature of the electrons, which we know very well how to measure.
Yeah. By the way, then my question is, for example, if you have a resonator and the resonator is in a thermal equilibrium of something, and then you introduce some two-level system coupled to somewhere else, and then you have leak of
absolutely
energy. And will it, for example, break the thermal equilibrium distribution of photons or not?
Yeah.
So
well, then you have like two different baths in a sense. You have the bath which we put on the chip intentionally, and then the photons if they leak to somewhere else. So then the distribution in the qubit is determined somehow by the competition of these different leakages or couplings.
Yeah, this is not so trivial question, but it can be straightforwardly again simulated with Q-tip. That's easy to do before doing the experiment. And see the dynamics, by the way. The dynamics is the most interesting.
Because in very rough terms, if you want to do this qubit thermometry, the thermometer should be coupled, or there should be a stronger coupling between those things than to some unknown bath where the photons leak.
Okay.